Good morning, dear children. Today we have to start the next topic, addition of vectors. Can you hear me? Okay, now let us consider a vector AB. A vector AB means a displacement from a point A to a point B. So this is vector AB. And now let us consider this point B. From here we are moving to another point C. From B to C. Then the net displacement from A to C is AC, the vector AC. See now, vector AB means it is the displacement from A to B in this direction. And here from B to C, vector BC means from B to C. Then the total displacement or the net displacement is from A to C. This is known as triangle law of vector addition. Triangle law of vector addition. See, here the direction is opposite direction of this. Here we are considering anti-clockwise direction, but here it is in clockwise direction. If AB, vector AB and vector BC represent the sides of a triangle, then the sum of the vectors AB plus BC. AB plus BC. See, here in this one, the initial point of vector AB is A and the terminal point is B. and this terminal point must be the initial point of the next vector, that is from B to C. Here the terminal point of vector AB is B. Here the initial point of vector BC is B. Then their sum is represented by the third side of which is the third side of the triangle in opposite order. This is the triangle law of vector addition. Vector AB plus vector BC, which is equal to vector AC. AB plus BC is equal to AC. Is it clear? Okay, now if we are considering this relation AB plus BC is equal to AC. You know that this AC is equal to minus vector CA because the direction is in the opposite direction. CA means it is in this direction. So AC is equal to minus vector CA. Transposing this to left side, AB plus BC plus vector CA, this is equal to 0. See, if we are considering the sides in the same direction, AB plus BC plus CA, then the net displacement is 0, which is represented by the vector 0 vector, or you can write this as AA, vector AA. So the triangle law of addition of vectors, once again, AB and BC are the two sides of a triangle. Then AB plus BC vectors, the sum of the vectors AB and BC, AB plus BC is defined as AC, which is the third side of the triangle taken in the opposite order. Here these two sides are taken in anti-clockwise direction, but here in this one AC is taken in clockwise direction. And if we consider this also in the same direction of these two, taken in order, that is AB plus BC plus CA, then the net displacement is 0, which is denoted by 0 vector, or it is AA. Both the initial point and the terminal point are same. Is it clear? Okay, now let us move to the next one. Suppose we are considering two vectors AB and BC if we are considering a vector equal in magnitude of this BC but in opposite direction, equal in magnitude but in opposite direction, then AB plus this BC, let us consider BC as B, vector B, and this as vector A. Then this BD is with same magnitude and opposite direction. So how can you represent this BD? Vector BC is B. So how can you represent this BD? This can be represented by minus vector B, and by triangle of vector addition here AB plus BD, this is equal to A plus A plus minus B, or this can be defined as A minus B. For finding the difference vector A minus vector B, we can apply the triangle of vector addition. This is the difference A minus B. BC is the vector B. So in opposite direction if we consider this, then it will be equal to minus B. Then by applying triangle law here, AB plus BD is equal to AD. AB is vector A and BD is minus vector B. So A plus minus vector B equals A minus B. So the difference can also be defined using triangle of vector addition. Okay, now the next topic is parallelogram law of vector addition. See, now here in triangle of vector addition, the initial point of a vector must coincide with the terminal point of another vector. Then we are applying the triangle of vector addition. In parallelogram law of vector addition, let us consider this. If we have two vectors, A and B, vector A and vector B, represented by the two adjacent sides of a parallelogram, then their sum A plus B is represented by the diagonal of the parallelogram passing through the common point of the given vectors. Passing through the common point of the given vectors. So here two vectors A and B are represented by two adjacent sides of a parallelogram. So here this is vector A and another one vector B. So to complete this parallelogram, see here, these two vectors have the same initial point. Vector A and vector B have the same initial point. So the common point here is, let us take this as A. Now, by parallelogram law of vector addition, the sum of these two vectors A and B is the diagonal which passing through the common point. The common point of the vectors is A, so the diagonal is AC, and this is represented by A plus B. This is the parallelogram law of vector addition. So if you have to apply the triangle law, one vector is AB, its terminal point must be the initial point of the second vector. But here it is not like that. Both the initial points are same. The two vectors have a common point and it is the diagonal. Then we are applying parallelogram law and the sum is represented by the diagonal of the parallelogram. Parallelogram law, is it clear to you? Can you differentiate the conditions when we have to apply the triangle law of addition and parallelogram law of vector addition? Okay, let us move to the next one. Properties of vector addition. Properties of vector addition. First one, for any two vectors A and B, for any two vectors A and B, A plus B is equal to B plus A. For any two vectors A and B, A plus B is equal to B plus A. Can you say which is this property? You had learned this property in case of numbers, whole numbers or rational numbers, real numbers, whatever it be. Okay, it is the commutative property. Commutative property of vector addition. Now the second one, for any three vectors A, B and C, A plus B plus C is equal to A plus B plus C. A plus B plus C is equal to A plus B plus C. Which is this property? It is associative property, okay? Associative property of vector addition. So the first one is for any two vectors, vector A plus vector B is equal to vector B plus vector A, and then for any three vectors A, B and C, A plus B plus C is equal to A plus B plus C. Now the third one is for any vector A, we have a zero vector such that vector A plus zero vector is equal to vector A. A plus 0, vector A plus vector 0 is equal to vector A, where 0 vector is called the additive identity. Is called the additive identity. So these are the three properties for vector addition, that is for any two vectors A and B, A plus B is equal to B plus A. For any three vectors A, B and C, the associative property is A plus B plus C is equal to A plus B plus C. And then 0 vector is called the additive identity as A plus 0 is equal to vector A. Moving to the next topic, multiplication of a vector by a scalar. Multiplication of a vector by a scalar. let A be any vector and lambda be a scalar. Then the product of vector A and the scalar lambda is denoted by lambda vector A is a vector collinear to vector A, is a vector which is collinear to vector A. So what are collinear vectors? What are collinear vectors? Simply alka that are collinear points. You are saying about collinear points. Okay, Chaitanya and Tirtha. See, collinear vector means parallel vectors. Simply we can define it like that. Not to consider the magnitude or direction, but the vectors which are parallel to the same line. Definition is parallel to the same line. We can simply say that parallel vectors. For example, see, this is vector A. Okay, another vector which is half of this. Half of this. This vector is represented by half vector A. So these two are parallel to the same line, or they are parallel to each other. Okay, or we can consider another one. This is 2A, 2 vector A. Or we can consider another one. This is minus 2 vector A. Okay, all these are parallel to the same line. That means they are parallel to each other. So these are collinear vectors. See, here in this case lambda is 1 by 2. Here in this case lambda is 2. Here in this case lambda is minus 2. So when we multiply a vector by a scalar, we are getting parallel vectors. And the direction of the vector lambda A will be same if the value of lambda is positive, and the direction will be in opposite if the value of lambda is negative. Is it clear? Direction will be the same according to positive values of lambda, and direction will be opposite as the value of lambda is negative. the vector lambda A has the same direction of vector A if lambda is positive and the vector lambda A has opposite direction of vector A if lambda is negative. So if a vector is a scalar multiple of another vector, you have to remember that they are parallel vectors. So instead of parallel vectors, we are using the term collinear vectors. I hope this is clear to you. So the next one is components of a vector. Components of a vector. For that, let us consider x-axis, y-axis and z-axis here. X-axis, y-axis and z-axis. Let us consider a point A on this x-axis whose coordinates 1, 0, 0 and a point B here on y-axis. Coordinates of B are 0, 1, 0 and coordinates of C 0, 0, 1. Let us consider these 3 points. This is the origin which is represented by O. Here OA is a vector in the direction of x-axis, along x-axis, and the magnitude of this OA, which is represented by modulus OA, is 1. See, since this point A is 1, 0, 0, the distance from the origin is 1 here. So magnitude of OA is 1 unit. That is, vector OA is a unit vector along x-axis. Here OA is a unit vector along x-axis. And it is denoted by I cap. See, OA, this is the vector having magnitude 1 unit and it is denoted by I cap. It is along the x-axis. Similarly, OB is a unit vector along y-axis. OB is a unit vector along y-axis which is denoted by J cap, and OC is a unit vector along z-axis denoted by K cap. So the unit vectors along x-axis, y-axis and z-axis are denoted by I cap, J cap and K cap. Always remember this notation. I cap means it is a unit vector whose magnitude is 1 along the x-axis, in the direction of the x-axis. J cap is a unit vector, that means magnitude is 1 unit along the y-axis, and K cap is a unit vector along z-axis. Let P, X, Y, Z be a point then the position vector of P denoted by OP, position vector of P denoted by this OP is given by xi plus yj plus zk. See, x, y, z are the coordinates of the point P. Then the position vector of this point P is given by, position vector means if we are considering a point P here, position vector means it is the vector from this O to P. This vector OP is the position vector of the point P. It can be represented as xi plus yj plus zk. Xi plus yj plus zk, where x, y and z are called the scalar components see, this is OP is equal to xi plus yj plus zk is the component form of vector OP. Component form of vector OP, where x, y and z are called the scalar components and xi, yj and zk are called the vector components. Are called the vector components. So if the position vector of OP is denoted by vector R, this is equal to xi plus yj plus zk. Vector R is equal to xi plus yj plus zk. Then modulus of vector R is given by root of x square plus y square plus z square. Modulus of vector R is given by root of x square plus y square plus z square. So this is a very important topic in this vector algebra. The component form of a vector is xi plus yj plus zk, where I, j and k are the unit vectors along x-axis, y-axis and z-axis. You can represent this position vector of a point as vector r, which can be written as xi, where x is the x coordinate of the point and I cap is the unit vector along x-axis, y is the y coordinate of the point and j cap is the unit vector along y-axis, z is the z coordinate of the point and k cap is the unit vector along z-axis. Then modulus of vector r is equal to root of x square plus y square plus z square. Is this clear? Okay, let us move to the next one. Let us see how can we add two vectors in component form. If vector A and vector B are given in component form, as vector A is equal to a1i plus a2j plus a3k and vector B equals b1i plus b2j plus b3k. Then vector A plus vector B is given by, we have to add the scalar components of corresponding scalar components. Okay, here a1 plus b1, a1 plus b1i, then plus a2 plus b2j, then plus a3 plus b3k. This is how we are adding two vectors which are given in component form. So the difference can also be defined like this. It is a1 minus b1i plus a2 minus b2j plus A3 minus B3K. This is how we are doing addition and subtraction if the vectors are given in component form. Now two vectors A and B are said to be equal. A is equal to vector B if and only if. Symbol for if and only if. A1 is equal to B1, A2 is equal to B2 and A3 is equal to B3. Two vectors A and B given in component form are equal only if their corresponding components are scalar components are equal. That is A1 equal to B1, A2 is equal to B2, A3 is equal to B3. So here vector A and vector B are given in component form where A1, A2 and A3 are called the scalar components. A1i, A2j, A3k are called the vector components. Then B1, B2, B3 are the scalar components of vector B. Then B1i plus B1i, B2j, B3k are called the vector components of vector B. Then we define addition and subtraction of vectors. Then two vectors are equal only if their corresponding scalar components are equal. Now let us see what is the multiplication of vector A by a scalar. Lambda A lambda A1i plus lambda A2j plus lambda A3k. This is how we are multiplying a vector A given in component form as A1i plus A2j plus A3k multiplied with a scalar lambda. We have to multiply the corresponding scalar components with lambda. And also we can define the distributive property here. Let A and B two vectors and K and M be any two scalars. Then K vector A plus M vector A can be written as K plus M vector A. Ka plus Ma. This is the distributive property here. K and M are two scalars. So Ka plus Ma is equal to K plus M vector A. Then K into M vector A is equal to km into vector A and then k into vector A plus vector B is equal to k vector A plus k vector B. These are the distributive properties while multiplying by scalars. Now the next is, if vector A is equal to a1i plus a2j plus a3k, a1, a2 and a3 are also called the direction ratios of vector A. A1, A2 and A3 are called the scalar components. The same times these are the direction ratios of vector A. And if this a1 square plus a2 square plus a3 square is equal to 1, a1 square plus a2 square plus a3 square is equal to 1, then a1, a2 and a3 are A1, A2 and A3 are called the direction cosines. So with this I am concluding today's class. Thank you.